Okay, so we'll move to the next session of this workshop, so which will be about the source processes of great earthquakes. And the first speaker is Claudio Satriano, and he will speak about the Rupture complexity of great earthquakes and its effects on seismic radiation.
Thank you, Martin. Hello to everyone. So I will present you some work we made at IPGP since several years in collaboration with many people you see there, like Martin Vallet, Raphaël Grandin, Pascal Bernat, Jean-Pierre Villotte, and student also Marina Corradini and Tristan Delplanque, with other contribution from other people at IPGP and also in Japan and in France. I apologize with the expert in the room, but we saw that it was more general public presentation, so we start with a small primer on the seismic spectrum in order to try to explain why we are interested in seismic radiation and why this is connected to the complexity of the earthquake rupture. So it is well known since the early days of seismology that the largest is an earthquake, the more effective this earthquake is in generating long period waves. Here I illustrate this with the recording of two earthquakes occurring in Southern California at the same spots and recorded at the same station 100 kilometers away. And you can see like the smallest one, 3.6, how it compares to the largest one, 5.8, which is able to generate longer period waves with respect of the smallest one. The seismogram is a representation of the energy radiated by the source and filtered by the propagation effect and the instrument. And it's a classical result in seismology that in far field, so when we are far away from the source, what we record is basically proportional to the slip acceleration, to the slip rate on the fault, what you see here. And basically, so properties like the characteristic source duration or the rise time affect the spectral properties of the ground motion we recorded in the far field. And of course, if there is some complexity in the source, like for instance, some high frequency content, we should find this complexity also in the far field recording. And another important property is that this slip on the fault is related to the seismic moment, the moment of a double couple of forces which acts on the fault by a simple relation. This relationship between the properties of the source and the properties of radiation has been formalized in 1967 by Keiaki in his seminal paper on scaling low seismic spectrum, which stated two important things among all. The first is that the seismic spectrum has a characteristic omega squared shape. So if we take the Fourier transform of the moment rate or slip rate, what we call the source time function, we get a shape like this with a plateau, a low frequency plateau, then a characteristic frequency, and then of cutoff, and then a high frequency decay f minus 2 or omega, which is the angular frequency minus 2. And the second thing is that the seismic spectrum is similar, so that there is a scaling relationship between the seismic moment and the corner frequency to the power of minus 3, as it is illustrated here for earthquakes of different magnitude. These properties have been verified in many real cases. I just show you some results from Herman Prieto, 2004, which shows the characteristic spectral shape as well as this omega or FC minus 3 scaling. And also from a theoretical point of view, it has been demonstrated, for instance, by Brun in 1970 and Raul Madariaga in 76, that a simple model like a circular crack can explain this spectrum basically with a characteristic frequency which is related to the source radius, A, here, and with low part which is related to the total energy, to the total moment associated with the rupture, and high frequency radiation, which is basically this simple model associated with the rupture, the radiation from the border of the circular crack. But of course, there is plenty of geological, geodetical, and seismological evidence that earthquakes, especially large earthquakes, are not simple cracks like this. So there is another kind of models for the seismic slip on a fault, which explain this spectrum, which are the so-called K-squared models, where the slip on the fault, now it follows a characteristical distribution in spatial wave number, which mimics this distribution in frequency. So there is a characteristic wave number, characteristic size, but then there is a lot of other scales, and the spectrum is similar here, which justify the high-frequency radiation. And this is very interesting because it captures an important point, which is the point of my talk, is that this high-frequency radiation in the real, in realistic earthquake models is related to the rupture complexity, so what happens at the smaller scales on the fault. So in my presentation, I will show you some observational evidence of this rupture complexity. So observation on this side of the seismic spectrum. And I will talk mainly about 3 earthquakes, which I put here on a global seismic hazard map. So the Great Toko earthquake of 2011, the Nepal Gorkha earthquake of 2015, and which is a little bit smaller, and another earthquake which is not probably well known with respect to the other 2, which occurred in 2013 in the Scotia Sea here, so north of Antarctica. And I will very briefly talk also about Maole and the Iquique earthquake, already talked about in the previous presentations. So let's start with the Toko earthquake. This is one of the largest earthquake which has been recorded in modern times, magnitude 9.1, which ruptured basically the whole, a large part of the subduction zone in northwestern Japan, with a huge coseismic slip. In the model here we developed is around 50 meters, the maximum slip. And here, so I show you a coseismic slip model of this earthquake, which is basically a reconstruction of the space-time history of slip on the fault, as you can see here from several snapshots. And in this particular case, we obtained this model by fitting, so by trying to reproduce the teleseismic waveforms at these stations. So what is important here to note is that for this analysis, we are in this frequency range, so between 002 and 03 Hertz, which is basically around the corner frequency of this earthquake. So we start seeing some complexity. The earthquake is not just a simple crack, but yet this earthquake is remarkably simple, seen from the slip point of view, with a huge but compact zone of a large slip, and maybe a second zone of a later slip, which comes basically after 100 seconds to the south. Now, what is interesting is that when you look at this earthquake from another point of view, so from the point of view of a strong ground motion recorded at a very dense seismic network in Japan, we can see that the complexity of this earthquake emerges. So here again is the slip model we developed, and this is a model by Lee and co-authors 2011, where they look at the recordings at a series of stations along a line roughly here in Japan, and they identified at least in the acceleration recorded at least 5 sub-events, 1, 2, 3, 4, and 5, which they try to locate on the plate interface. So we see that we have a complex rupture with at least 5 sub-events, and the other big difference with this is that the sub-event seems to be closer to the coast with respect to the large slip area, and therefore if we imagine the subduction more deeper in the subduction zone. So in Japan, we are lucky enough to have a very dense seismic network. This is not often the case, so it's nice to have also other tools to try to image this complexity from, for instance, from teleseismic distance. And this is one of the advantages of the back projection method, for which I show you an application again to the Toko earthquake. So with back projection, we basically take advantage of dense networks deployment at teleseismic distance, like for instance the European network here, for which the waveforms recorded are very, very similar. This because basically the waveform propagation at this distance is basically in the upper mantle, so it's a zone which is not so heterogeneous for the seismic frequency we are observing. And speaking of frequency, here in back projection, in order to have some resolution, we have to look at higher frequency. So we are now higher frequency respect to the corner frequency. For instance, in this specific case, we are looking between 0.2 and 0.5 hertz, but we can also do as the case between 0.5 and 4 hertz, as I will show you. And what we imagine with back projection, we basically try to track the more likely sources of this high frequency energy by a simple approach. So we draw a grid here, and for every point of the grid, we test at a particular time if this point is a possible source. If this condition is true, then the waveforms will align to this travel time, and we will have a positive stack. Otherwise, a constructive stack. Otherwise, we will have a destructive stack, so no energy from the other points. And here, so you see the energy of this beam, we call beam the stack of these traces, as it progresses on the fault as a function of time. What we can do then is to take this kind of image to extract at every time the maxima of energy. This is what I did in this figure. So now here you see again the slip model and the maxima of back projection with the sides proportional to the energy we reconstruct by back projection. And the color now it's time from 0 to roughly 160 seconds. And what you can see is quite striking, is that there is a clear partition between the zone which produced the largest leap for the Tohoku earthquake and the zone which produced the high frequency radiation. So for me, high frequency again is between probably 2 seconds and 1 second of period, so 0.5 and 1 hertz, which is closer to the coast and so deeper on the subduction zone. And the other interesting thing is that those zones are quite remarkably well in accordance with the high frequency, the strong motion generating area identified by Lee and co-authors. So basically here we are in a sort of a worst case scenario where the bulk of the seismic moment is close to the trench, which is what excited the huge tsunami associated with Tohoku earthquake, whereas the high frequency which produced the waves which are more dangerous for structures and cities and houses in Japan are closer to the coast, are closer to Japan. So it's really the worst case scenario for an earthquake. And now I want to rejoin a little bit what Marianne Metois was saying in her first talk. In order to have a clue on what on the fault can control this dichotomy between low frequency sleep and high frequency radiation, it's very interesting to go and try to look at the background seismicity, so the calm before the storm, as Marianne was saying. So what happens in the interseismic period with respect, so before this large earthquake. So here I plot a series of things. Okay, this is again the rupture zone of the main slip of Tohoku. And here those smaller patches are the rupture areas of smaller earthquakes. There's earthquakes between magnitude 7 and magnitude 8. And also put the background seismicity recorded between 1980 and 2011. And repeating earthquakes. Jean-Mathieu talked a bit about this in his talk, which are basically indicate smaller asperity which rupture quite regularly. And what we can see is that the most part of these intermediate sides rupture occur in the deeper part of the subduction, so close to the coast. And there is a second group of these events which occurs on the second level, I would say, but not that close to the trench. And when we look at the repeaters, which are basically indicate probably small rupture which are embedded by creeping environment, we see that most of them are at the base of what is probably the coupled zone, marking a frontier between a coupled and totally decoupled zone, but also abundant in this zone here of the subduction, which is a quite complicated zone because we have a junction between the Pacific plate, the Okhotsk plate, and the Philippine Sea plate. And again, we see that there is a correspondence between these ruptures, the repeaters, and the high-frequency radiators from back projection. So this led us to propose simple model, conceptual model for this subduction. So suppose that here now you see a cut of the subduction going roughly like this here. And basically, you have two zones. You have, which are marked by a frontier, which is the mantle wedge, which is here. You have a zone of deep ruptures, where deep ruptures repeat in time, and also repeaters repeat in time. And the second zone where these magnitude 7 ruptures occur. And probably this zone is, due to the repetition of these earthquakes, is characterized by basically a heterogeneous stress state. We can imagine that the repetition of these earthquakes perturbs the stress state of this zone, and this heterogeneous stress state can influence the radiation of a big earthquake like the one of Tohoku when it enters this zone, and the rupture interacts with this pre-stress condition. And the other thing which is interesting is that those ruptures, they never pass this kind of frontier, which can be associated probably with the bending of the fault plate, and only from time to time huge ruptures like the Tohoku one can pass this frontier and propagate to the trench in a zone which is not that seismically active, so which can be interpreted like a zone which has or which is transitioning with towards a strengthening friction. So it's a zone which cannot nucleate earthquakes but itself, but which can be drawn into motion if a sufficiently large earthquake, which nucleates everywhere, somewhere else, penetrates into this zone. So the important message to me, at least here, is that background seismicity and large earthquake ruptures can inform us on the mechanical state of the plate interface. This is a little bit also what Marianne was saying. And this information can be useful, maybe use to forecast the rupture and radiation properties of future large earthquakes. Now, these kind of properties have been observed also for other earthquakes worldwide. Here I present you very quickly two other results of mine, but many other authors have obtained basically the same results. This is the Maule earthquake. We talked about it in the previous presentation. Again, you can see a partition between large slip and high frequency radiation, which is again in the deeper part of the subduction. And this is the Iquique earthquake, where I put you the rupture zone of the main shock, 8.1, and of the aftershock, 7.7. And again, you see that high frequency radiation is basically associated with the rupture stopping at the deeper part of the subduction. And here I also put a coupling map of Marianne, which show quite well that basically the rupture stops when the plate interface decouples. And maybe this high frequency radiation, so we can interpret it also as an abrupt, so like a stopping phase, an abrupt rupture arrest at this decoupling zone with emission of a high frequency radiation. And this has been also explained by Thornley in a well-known paper of 2012, where he says that basically when we look at the subduction zone, the frictional properties of the subduction zone, they change as a function of depth. So basically we have a zone of large asperities which can produce these megathrust earthquakes, and a deeper zone of smaller asperities which can produce smaller earthquakes during the interseismic period, and high frequency radiation during the large earthquakes rupture. And then maybe in a seismic zone close to the trench, which can drawn into motion by ruptures occurring here, and or produce tsunami earthquakes close to the trench. The second earthquake I want to talk to you about is the Gorkha earthquake, which occurred in Nepal in 2015. This is very interesting because it's occurred at a continental thrust, a continental collision. And so it's very nice for our point of view, because we have basically an observation of this earthquake from the top, which is not possible with subduction earthquakes occurring at sea. And this earthquake partially ruptured what is supposed to be a seismic gap. And which supposedly ruptured a zone which was ruptured in 1833. The city of Kathmandu is here, so close to the southern edge of the rupture, or the up-deep edge of the rupture, and this is the epicenter. So this earthquake produces a death toll of 9,000 people, probably a dozen of them killed by landslide, but this is a death toll which is much lower what we should expect from the magnitude of this earthquake, and especially the distance of, for instance, Kathmandu from the main slip area. And this can be partially explained by looking, for instance, at the signal recorded in Kathmandu from one accelerometer. Here I just show you one component, which is characterized by some very low frequency oscillation, which is probably related, as I will show you later, to a basin effect in the Kathmandu Valley. But we also see that, seen from Kathmandu, this earthquake seems depleted in a high frequency content. And this is kind of dramatically illustrated by this movie, probably some of you have seen. I tried to roughly synchronize it with the seismic signal, which show like people are moved like they were on the deck of a ship where this low frequency wave arrives. So again, this is probably a basin resonance effect. But the other important point here is that you can try to guess the poor quality of the construction in Kathmandu, and yet most of these buildings resist this earthquake. Again, testifying probably the low frequency content of this earthquake. But I have to say this has been well studied by, in this paper by Rajaur and colleagues, to which Susan and Pablo here participated. They basically show two things. The first is that when you look at the intensity, in the end it's quite relatively low intensity compared to in the whole slip area compared to the magnitude of the earthquake. And the other thing is that they retrieved several accelerometric records. Here I just show you two, one on a rock site and the other one on the soft soil site. And they applied a standard, a typical analysis in seismic engineering, so to compute a response spectrum, which is the response of a series of 1D oscillators. And this response spectrum was compared with the ground motion prediction equation, which shows that the small earthquakes, and this was done for two earthquakes, the largest aftershock 7.3 and the main shock 7.8, what they showed that the aftershock, it basically fits the theoretical prediction by the ground motion prediction equation, whereas the main shock, it's a low period, so at high frequency is below the ground motion prediction, so it's depleted in a high frequency. And here for the soft soil site, you can also see the basin resonance at a longer period. For this event, we, together with Martin and Raphaël Grandin, we constructed a kinematic slip model. This model was constrained by INSAR, Interferometric Synthetic Aperture Radar, which is very useful here because the earthquake is completely ground and the fault plane is very flat in the end, but also from static and dynamic GPS, so local ground motion from GPS and accelerometers, and by teleseismic waveforms. What we obtain is a slip model which is very similar to what other authors obtained, which testifies the fact that basically this kind of data really constrains the slip model. And the slip process, which is very simple, it's a very pulse-like process, again, in accordance with other authors, which emanates, of course, from the hypocenter and then propagates eastwards. What is interesting is that when we perform back projection of this event, this time using 3 different arrays, the 3 results, in fact, agrees, again, in saying that the high frequency comes from the base of the rupture, so from the deeper part in the subduction zone. This, in a sense, explains the fact that in Kathmandu, the high frequency signal is somehow lower than what we expected. And another way of looking at this is that if we take our kinematic model, which was obtained by inverting data up to 10 seconds, this model can easily fit the data in Kathmandu up to 1 Hertz. So again, testifying the fact that a simple kinematic model can it's enough to explain the ground motion in Kathmandu. So how can we explain this? We can try to use the same framework we use for subduction earthquakes. So here I show you again the slip zone of the Gorka earthquake, the back projection. And this is the background seismicity. And also on the background, you see the seismic coupling, which was computed by Raphaël Grandin using GPS data and leveling data here. And what you see again is that the rupture stops, and the high frequency also occurs in a zone where the interface decouples. So the couple moves from almost 100% to almost zero. And this zone here also associated with the structural variation of so in the dip of the subduction plate here. And this zone is also a zone where there is a concentration of background seismicity. This is seismicity between 1995 and 2003, which could also be associated again to a stress concentration, which is again a factor which can influence the high frequency radiation. And this is basically what I say here. The other puzzling thing here is why the rupture stopped here. It doesn't move up to the front here of this thrust. If the zone is coupled in the end. So what stopped the rupture, and why the rupture didn't stop abruptly? Because if it stopped abruptly, we should have seen high frequency radiation coming from these sides. So maybe a possible explanation is basically in the same kind of idea what Jean-Mathieu was saying before, is that maybe full coupling does not necessarily mean weakening friction, but we could have some sort of a transition between weakening friction and strengthening friction here, which lets the rupture die a little bit slowly in this zone without emitting high frequencies, which means that we need a much larger earthquake to try to penetrate this zone and make all the way up to the thrust front. The last event I want to talk about is the magnitude 7.8 Scotia Sea earthquake. This is an event which occurred here, so north of the Antarctica Peninsula. It's very interesting because it's a strike-slip event which ruptured two segments. Strike-slip events are simple enough to be modeled with 1D slip models. So this is a slip profile along this event. So you can see that there are two segments and basically no slip within these two segments. And when we do back projection from station situated here, what we see is that the back projection peaks are basically associated with the start, the stopping of the rupture here, the restart of the rupture, and the stopping of the rupture here again. And maybe a second peak which can be associated with the variation in the slip here. So it seems to be a good relation between fault segmentation and high frequency radiation, if we interpret this like rupture, acceleration, and deceleration. And even more strikingly, from my point of view, is that when we look at apparent source time function, so those are slip rate function as seen from different stations all over the world, and since the rupture basically goes in this direction, we have directivity effects which change the relative length of this function. So of course we see this directivity effect, but the other things that we see is that when we put the arrival times associated with these back projection peaks, they quite nicely coincide with moments with slip basically decelerates or accelerates. So where it's basically, in my opinion, associated with the derivative of slip rates. So it seems that the high frequency radiation measured by back projection using velocity recordings, I have to see this in a far field, seems to be associated with slip acceleration. And this motivated us to do some synthetic study, which is the objective of the PhD project of Marina Corradini, who will present a poster this afternoon, where we, again, suppose a very simple linear fault. We put it here because we can put it everywhere, it's a synthetic test, but here we have 3 arrays all around. And what she did is to simulate a very simple rupture where everything is homogeneous, and then to try to put some heterogeneities, for instance, in terms of final slip or rise time or rupture velocity. And what we see is of course kind of expected if you put a very simple model, so kind of a Haskell fault. What we see is basically radiation This is a simple sample signal which comes from the beginning at the end of the rupture. This is numerical noise. And in this kind of plot, basically you have space here and time here is a 1D problem, so we can plot it in 2D with space and time. And what you see here, you have a radiation at the beginning, at the end of the rupture. And what you see also, you see the rise time as 2 peaks here. And this is nicely associated with slip acceleration or the spatial derivative of slip rate on the fault. And as soon as we introduce some complexity, for instance, slip rate here, we find this complexity from the back projection analysis. And again, in these very simple models, it corresponds nicely to variation in space and time of slip. And of course, if you want more details, please come to the post of Marina this afternoon. So to conclude, the high frequency content of radiation from earthquake rupture seems to be controlled by the variability of the mechanical properties in the fault zone. So the coupling, the presence of asperity, geometry, but also the pre-stress condition. And as Marianne also said, the study of seismicity and deformation before large earthquakes seems to be a necessary tool to characterize these properties and try to anticipate the rupture properties of future large earthquakes. And new imaging techniques like the back projection can help in illuminating this complex nature of the earthquake rupture, but we need still to better understand the link between high-frequency image and the rupture process. Thank you.